The Baltic Sea looks calm from above, flat water, gray horizon. Nothing unusual, but somewhere beneath the surface, engineers are attempting one of the most precise construction operations ever attempted. They are lowering concrete structures the size of skyscrapers onto the floor of the sea. Each one weighs 73,000 tons, and when they land, they must align with the one before it, not within centimeters, within 2 millimeters, less than the thickness of a coin, 40 meters underwater. This is the Fehmarnbelt Fixed Link, and it may be the most precise underwater megaproject ever built. To understand why this tunnel exists, you need to look at a map. Denmark sits at the top of the European continent, a peninsula reaching northward, surrounded by islands. Beyond it lies Scandinavia, Sweden, Norway, Finland, and between Scandinavia and the rest of Europe, a body of water, the Fehmarnbelt Strait, about 18 kilometers wide, not enormous on a map, but for a freight train traveling from Hamburg to Copenhagen, this gap adds hours. Today, that journey requires a ferry crossing, one that can be delayed by weather, disrupted by wind, or simply slowed by the logistics of loading and unloading vehicles. For passengers, the crossing takes about 45 minutes. For freight, those minutes multiply across thousands of shipments every day. The tunnel changes that entirely. When complete, a train will cross the Fehmarnbelt in under 10 minutes. The total journey time between Hamburg and Copenhagen will drop from roughly 4.5 hours to under 3. This is not a vanity project. It is critical infrastructure, a permanent connection between Scandinavia and the economic heart of Europe. The tunnel will carry both high-speed rail and highway traffic. Funded and operated by the Danish state-owned company Fehmarn AS, and decades in the planning. But financing and politics are the easy part of this story. The real challenge begins 40 meters below the Baltic Sea. If you enjoy learning how the world's largest engineering projects actually work, consider subscribing to Next Build. We break down the physics, technology, and scale behind the mega projects shaping our future. Now, back to the Baltic Sea. When most people imagine a tunnel beneath the sea, they picture a tunnel boring machine. A massive rotating drum grinding its way through rock. That's how the Channel Tunnel between the UK and France was built, and it's how most undersea tunnels are constructed today, but the Fehmarnbelt Tunnel uses a completely different method, an immersed tunnel. The concept is surprisingly simple. You build the tunnel sections on land, inside a controlled factory environment, then you float them out to sea, lower them into a trench on the seabed, and connect them together, end to end, until a continuous tunnel forms beneath the water. In theory, it sounds straightforward. In reality, it is one of the most complex logistical operations in civil engineering. Why use this method instead of drilling? The answer lies in geology. The seabed beneath the Fehmarnbelt is shallow, between 20 and 40 meters deep, but the ground beneath it is unpredictable. Clay, sand, loose sediments, not ideal for tunnel boring machines. A bored tunnel would have needed to go much deeper to reach stable rock, which dramatically increases cost and construction time. The immersed tunnel approach allows engineers to build the full tunnel cross-section on land. Each Fehmarnbelt tunnel element contains 5 separate tubes, 2 for road traffic, 2 for rail, and a central corridor for maintenance and emergency access. The entire structure is 42 meters wide. Constructing something that large underground would require multiple parallel tunnels. But with immersed construction, everything is built as one enormous element, manufactured in a factory with strict quality control and precise engineering. The trade-off: you must transport 79 enormous structures across open water and place them perfectly on the seabed, one after another. Each tunnel element is 217 meters long, 42 meters wide, 9 meters tall, and weighs 73,000 tons. That's roughly the weight of 50 Eiffel Towers. Before any of that weight can be lowered to the seabed, it first has to float. This is where physics takes over. Archimedes' principle states that an object submerged in water displaces a volume of water equal to its own volume. If the weight of that displaced water is greater than the object itself, it floats. Concrete is heavier than water, but the Fehmarnbelt tunnel elements are hollow. Their 5 large internal tubes displace enough water to make the entire structure buoyant. Temporary steel bulkheads seal both ends of the element, creating a watertight structure. When the casting basin is flooded, the tunnel element floats, just barely. Only a small portion of the structure rises above the surface. From there, tugboats take over. Moving 73,000 tons of floating concrete across open water is not something done casually. Weather conditions must be perfect, wind speeds carefully monitored, ocean currents predicted. A fleet of tugboats surrounds the element, some pulling, some steering, others acting as stabilizers. The convoy moves slowly, barely faster than walking pace. Too fast, and the element itself begins generating waves that could destabilize it. When the structure reaches its destination above the trench, the most delicate part of the process begins: ballasting. Water is slowly pumped into ballast tanks inside the structure, gradually increasing its weight, until the structure becomes heavier than the water it displaces and begins to sink, very slowly. The descent can take several hours. During that time, the element is suspended by cables connected to a positioning frame on the surface, guiding it downward with extreme precision, because once it reaches the seabed, there is almost no margin for error. 2 millimeters, that is the tolerance engineers must achieve. When a new tunnel element approaches the one already resting on the seabed, the 2 ends must connect perfectly. Between them is a massive rubber gasket called an omega seal. This seal ensures the joint is watertight. For it to function correctly, the 2 concrete faces must align within 2 millimeters. Now, consider the conditions. You are positioning a 73,000-ton structure, the size of a city block, suspended in moving seawater, 40 meters below the surface, with currents pushing against every surface, visibility often near zero, and the target alignment is 2 millimeters. The positioning system combines GPS tracking on the surface with underwater acoustic transponders. Laser measurement tools monitor alignment. Hydraulic systems adjust the element's position by fractions of a millimeter. Engineers guide the structure slowly into place. Micro adjustments, tiny rotations, gentle nudges, until finally, contact. The omega seal compresses between the 2 elements. Water pressure pushes them together. Pumps remove water from the joint cavity, and suddenly, the connection is dry. 2 elements join together beneath the Baltic Sea. Workers then enter the tunnel interior. Steel tie rods lock the structures together. Grout is injected beneath the element, anchoring it permanently to the seabed. 1 element complete. 78 more to go. Construction of the Fehmarnbelt Tunnel began in 2021. On the Danish island of Lolland, engineers built one of the largest construction factories ever dedicated to a single infrastructure project. 9 parallel production lines manufacture tunnel elements simultaneously. Each one takes months to complete. Thousands of tons of reinforcing steel, carefully controlled concrete pours, temperature monitoring to prevent cracking during curing. Finished elements are moved into a giant casting basin, a temporary harbor constructed beside the factory. The basin floods, the element floats, the sea gates open, and the towing operation begins. Through 2025 and 2026, the immersion phase defines the project. Each element placed during carefully selected weather windows. Because the Fehmarnbelt Strait is also a busy shipping lane, coordinating massive marine construction with active commercial traffic adds another layer of complexity. The seabed trench itself was dredged with extreme precision, then lined with a carefully leveled sand layer. That sand bed acts as the final adjustment surface, allowing the element to settle into perfect alignment. Once all 79 elements are installed, the trench will be backfilled with gravel and protective rock, locking the tunnel permanently into the seabed Then comes the interior work: road surfaces, rail tracks, ventilation systems, emergency escape routes, communications, lighting, fire suppression. The target opening date is 2029. When that day arrives, the ferry crossing that once took 45 minutes will be replaced by a 10-minute train journey beneath the sea. There is something remarkable about projects like this. The Fehmarnbelt Tunnel will not be the tallest structure on Earth. It will not dominate the skyline. In fact, once completed, it will be invisible, buried beneath 40 meters of water and sediment. From the surface, the Baltic Sea will look exactly as it always has, but beneath it, 18 kilometers of precisely joined concrete, 79 elements, each aligned to within 2 millimeters, each lowered carefully into place by teams of engineers, divers, and operators working in conditions that leave no room for error. This is the quiet side of infrastructure, not the bridges that dominate postcards, not the skyscrapers that define city skylines, but the hidden systems that hold the modern world together: the tunnels beneath oceans, the cables carrying the internet across continents, the pipelines moving energy between nations. Infrastructure designed not for spectacle, but for reliability. 2 millimeters, 40 meters below the sea, 79 times. That is what it takes to connect two countries. If you enjoyed this deep dive into one of Europe's most ambitious engineering projects, subscribe to Next Build. We explore the mega projects shaping the future of infrastructure around the world. And if you want to keep watching right now, there's another mega project documentary waiting on your screen.